This video is on an introduction to acidic and basic solutions. We'll start with some very basic definitions for acids and bases. Now, there are several different definitions, but we're going to go over really the first one that we came up with. Now, when we were writing chemical formulas, we recognized acids because their formulas began with hydrogen. And that's because in this definition of an acid, it's any substance that increases the concentration of hydrogen ions in aqueous solution. So this definition is a little limiting because it has to be in a water-based solution, but that's how we do a lot of things. Also, those hydrogens must be able to ionize away or separate from whatever they were bonded to in order to be considered an acid. Sugar has a lot of hydrogens in it, but those hydrogens aren't able to ionize off of the other structure, so sugar is not an acid. Now, we have different types of acids, and it depends on how willing that hydrogen is to remove from what it was bonded to. So we kind of refer to them as strong or weak. Strong acids ionize 100%. So the example I have here is hydrochloric acid. Hydrochloric acid, when you put it in water, it is going to ionize. And this is a one-way arrow, so we're going to get a lot of hydrogen ions and a lot of chloride ions. I have this picture here, and you can imagine this, these molecules over here as HCl. So the yellow would be the hydrogen and the red would be the chlorine. And when we put it in water, what we see is those molecules do separate. And almost all of them, we've got a couple here that didn't, but we get a lot of hydrogen ions, all these little positives floating around in solution. That is what hydrochloric acid will do. Now, I want to mention something about this H+. This hydrogen ion is super attractive. I mean, so attractive, it will not spend a lot of time by itself. In a world where atoms are surrounded by electrons, H+ is just this positive proton floating around. So that's the reason it's so attractive. And if we get hydrogen ions in aqueous solution, they're around a lot of water. And so what really happens to this hydrogen ion is that it will bond to water and form the hydronium ion. And we did study that when we were looking in our polyatomic ions. So it's a little unrealistic to just kind of look at it as H+, because really floating around in solution, you're going to have water bonded to that hydrogen ion forming the hydronium. But this is a simplified way to look at it, and that's what we're going to focus on here in this class. Now, we have strong acids, and there aren't very many of them, only 6. So the rest of the acids are weak. And what that means is they do not ionize 100%. So what we have here is acetic acid. This is a major component of vinegar. That vinegar smell is the smell of acetic acid. And you'll notice the difference here in the equation. I have a double-headed arrow. That's because this hydrogen does separate from the acetate ion, but then it goes the other direction and they bond back together. So it's kind of a back and forth. I like to describe it as a high school relationship. So what we can see here in this picture is we've got our acetic acid here, the hydrogen bonded to the acetate ions, and when we put them in water, we don't get as many hydrogen ions floating around in this weak acid like we did in a strong acid. And that's because while some of them have split up, others have gotten back together. So what we have is acetic acid, and then it splits up, and then they get back together. And then they break up, and then they get back together. And then they break up, and then they get back together. And it's constantly, all the molecules are doing this. So if you were to take a snapshot, what you're going to see is not a lot of ions floating around, because while some have split up, others have gotten back together. Now, bases. Any substance that increases the concentration of hydroxide ions in aqueous solution is considered a base under this particular definition. So H plus is your acid stuff. OH negative or hydroxide ions are base stuff. And you need to go ahead and associate that in your head. So if something has hydrogens that can be given off, it's an acid. If something has hydroxide ions, it's a base. Now, oftentimes when you're looking at bases, you'll see the term alkaline, and that just means it is a basic solution. So you might have seen this, or you have seen this before in our class, the alkaline earth metals, the alkali metals. These guys, those metals, when they get in contact with water, which happens in nature, they form basic solutions, and that's how they named those groups of the periodic table. You might have also seen the term alkaline in referring to batteries. So AA, AAA, C, and D batteries are alkaline batteries. That's because they have these batteries don't have battery acid. That really only happens in a car battery. They have battery base. You may have even seen it sometimes if you leave batteries in an electronics too long and they form that white crusty stuff. That's usually the potassium hydroxide that has leaked out of there. Now, don't underestimate bases. Bases can be just as corrosive as acids. Most students at this age recognize that acids can be very dangerous. And they would, again, corrosive, they're going to be corrosive to the skin and would eat kind of through your skin, and it is quite painful. Bases, though, can be just as corrosive, just in a different sort of way. Bases, actually, if you were to get that on your hand, they are going to start working on the fat in your skin and in your body and turn it into soap while you're wearing it. And that's not a comfortable situation at all. All right, so alkaline means basic. Go ahead and associate those terms together. Now, just like with acids, we can have strong and weak bases. Strong bases, again, ionize 100%. So anything really that has a hydroxide in there is going to be a strong base. So we have lots of strong bases, and they will dissociate. So you get a lot of hydroxide ions floating around in solution. Weak bases actually kind of work in a different way. They kind of work with water and in that aqueous solution, and they're going to strip a hydrogen from water. And if you take a hydrogen away from water, all you're left with is hydroxide. And that's the way that they work. A weak base to know is ammonia. Now, this is in Windex, window cleaner, and a lot of cleaners tend to be either acids or bases. A lot of them are bases. Hand soap is basic. Bleach is basic. These guys are going to, ammonia loves to become ammonium, and that's what it's going to do in pretty much all reactions with ammonia. So it's going to try and strip a hydrogen away from anything it possibly can. So if you put ammonia in water, what it's going to end up doing is strip a hydrogen away from water to form that hydronium or that ammonium ion. And water, when it loses one hydrogen, becomes hydroxide. And that's how it is considered a base, because it does increase the concentration of hydroxide ions. All right, but not as many, because you will notice the double-headed arrow here. So ammonia takes the hydrogen, and then what's left of water says, hey, give me back my hydrogen, and it reverts back to this, and then it goes this way, and then it goes this way. So we set up a little equilibrium, and we'll talk more about that here in the coming days. Now, the pH scale does run from 0 to 14, not 1 to 14, 0 to 14. And below 7, so from 0 to 7, we have an acidic solution. Neutral is there right at 7, and then above 7 is considered basic. A solution that has a pH of 14 is pretty nasty stuff. This would be like straight sodium hydroxide, which is commonly known as lye, and used in soap making, but pretty nasty stuff. Drain cleaner pH of 14. A pH of 0 would be car battery acid, so sulfuric acid is very, very acidic. And so pHs on these extremes are going to be very harmful to you if you were to spill them on your skin. And so if you were to spill them, we would want to neutralize them. But we'll talk more about that in a later lesson.